Okay, let's move on to section 9.9 using second derivative. So the second derivative is the differential of the first derivative, and you've used it in the past to identify the type of a turning point, whether it was a maximum or minimum or point of inflection. So in general, when the second derivative was negative, then you were finding a maximum, and when the second derivative gave you a positive value, that would indicate that the turning point is the minimum. If it was equal to 0, then you needed to test the values either side of the turning point to establish whether it's minimum, maximum, or point of inflection. So if you look at the graph over here, what we got clearly at this point here, the second derivative will be negative. So at this point, f dash of x is negative because it's a maximum turning point. So this is a local maximum. Over here, that will be the local minimum, and the second derivative is greater than 0. And these are the only two extreme points, because here we've got an asymptote and then another asymptote. There is no turning point in this side. Now, when you're going along this curve, you are going to go, imagine going along and driving a car. If you were not turning the steering wheel, you will be actually going straight on that way. So you have to turn the steering wheel right all the way throughout the curve while you are drawing and passing this maximum point. So that motion of turning the wheel right tells you that the second derivative is negative. So you're kind of turning right. Now if you imagine traveling there, turning right, the shape you are going to draw is like a part of an oval shape. It's called a concave curve. You kind of have a cave here. There you go. So cave, you're drawing a cave. Now when you hit that point over here, the steering wheel, in order to carry on along this curve, you need to straighten the steering wheel so it heads on, facing head on, and then it starts turning left. Now over here, once you imagine turning a steering wheel left, that second derivative is always going to be positive. So this motion of turning left is happening. So turning right, straightening the steering wheel, and then turning left. The point at which the second derivative changes its value from positive to negative or negative to positive, like over here, where you have to reach the middle value and then turn left or right, that is called the point of inflection. Now you've met points of inflection last year that looked like this. So usually they had also the gradient was 0. So if you imagine turning right, so it's like a concave curve, and then straight on, and then left. You change the way you're steering. So this means you change the sign of the second derivative from negative to positive, and therefore that is also the point of inflection. Now like this one here, you can imagine as a cave. This is the other one. It's not a cave. It's called convex curve. And it carries on all the way through, reaching, trying to get closer and closer to this asymptote. Now when you jump across, okay, so when you jump over the asymptote and you start your journey on the other side of the curve, you are going to be turning left again. The steering will have to sort of be turned left. That means the second derivative is greater than 0, so we have a convex curve. Okay, so let's have a go at the first example on this idea. So 24, here's a cubic, and we are asked to find the interval on which the function is concave. So remember concave, maybe quickly draw that. That's a concave. We've drawn a cave. So you are inside a hill, there's a cave there. You've got the maximum, and remember when you have a maximum, the second derivative is negative. So concave, you've got a negative second derivative. So they are telling you to differentiate the function twice and then solve the inequality when it's less than 0. So that is the first derivative, and there is the second derivative, so it's 6x. So the second derivative is less than 0 when 6x is less than 0, and that happens for x less than 0. So the interval is going to be x's belonging to real values and x is less than 0. It could be equal as well. I think both are acceptable, but when it's equal, you are going to hit the point of inflection. So really, either that or you could put an equal as well. Both will be acceptable. And now this is a set notation. The interval notation, well, interval notation is going to be anything from -infinity up to 0. If you want to include 0, you give it a square bracket. If you don't want to include 0, you put a curly bracket. Okay, so going to move on to example 25. That example is over here. Now we are asked to show that this particular curve, e to the power of 2x plus x squared, is convex for all real values. So remember, convex, and draw the convex. It's a smiley face. It's got a minimum, possibly minimum, but this is how I remember. So that means the second derivative needs to be greater than 0. So let's find the derivative. The first one to begin with, so it's 2e to the power of 2x plus 2x, and the second derivative is the second. Example 2 comes together with that 2 to become 4e to the power of 2x plus 2. Okay, so this expression over here, this is 4e to the power of 2x plus 2, is always, not always, only always positive, it's always greater or equal to 2 as well. So it's always above, it's actually not equal to 2, it's always going to be above 2, so it's always positive. So e to the power of 2x is always greater than 0, therefore 4e to the power of 2x plus 2 will be always greater than 2, therefore it is convex for all x belonging to real values, because e to the power of x is defined for all real values, and so is e to the power of 2x plus 2, 4e to the power of 2x plus 2. Okay, for example 26, you've got a cubic. We're going to show that it is concave on the interval starting from -2 up to 0, including the endpoints, they say, and convex on the interval 1 to 3. So let's test the second derivative. So find the first one. That is going to be 3x squared minus 4x minus 4. The second derivative is given by 6x minus 4. So 6 x minus 4 is going to be concave. Remember, this is the cave, so it's going to be the second derivative must be less than or equal to 0, depending what approach you want to adapt. 6x. I think I may have copied the example incorrectly. Oh, okay, that's fine. Misread it. So x is less than 2/3 here. That's going to be concave. And convex, that's going to be for x is greater than 2/3. So as you can see, here's 2/3. There is 1, it's going to be here, that's 0 minus 2. So between minus 2 and 0, this is completely below 2/3. So that means between minus 2 and 0, it's going to be concave, and between 1 and 3, that's above 2/3. That means it's going to be convex, because all the values between 1 and 3 are greater than 2/3. So that's going to give you convex solution, and for all the values between minus 2 and 0 are less than 2/3. So that's going to be concave. That's a strange question. Okay, to find the point of inflection, we need to find the when the second derivative changes its value from positive to negative. So you could see from before it happened for x equals to 2/3. So all we need to do is to find the corresponding y coordinate. So substituting 2/3 into the y function, we are going to get the answer of 47/27. So it's 2/3 and 47/27. There you go. Let's have a go at example 26. So here we are going to look at points of inflection. So remember, points of inflection, from what I said before, will be those that where the second derivative changes from positive to negative or negative to positive, so when it's equal to 0. So in the first part, we need to show that the function is concave on the interval minus 2 to 0 and convex on the interval 1 to 3. So as soon as they mention concave or convex curve, I know they're asking me to differentiate twice to find the second derivative. So this is the first derivative, even 4, and then d2y dx squared will give me 6x minus 4. So 6x minus 4 is the second derivative when it takes negative values, and that will happen for when 6x is less than 4, so x is less than 2/3. That means, remember, when it's negative, you are just imagining a hill, so we are going to turn right. This is a cave, so it's concave. So obviously, when it's greater than 2/3, it's going to be convex, and that will happen for x is greater than 2/3. So looking at this, there is 2/3. So anything to the left of 2/3 will be concave curve, and convex on this side. So if you could see that clearly, minus 2, anything between minus 2 and 0 is clearly less than 2/3. So as minus 2, 0 interval is less than 2/3 the curve is concave, as anything in the interval 1, 2, 3 is greater than 2/3 the curve is convex. There you go. Now for part B, we need to find the point of inflection. So point of inflection is where the curve changes from concave to convex, and it clearly happens when d2y dx squared is equal to 0. So for x equals to 2/3. So we just need to find the corresponding y coordinates. So sub the 2/3 into the y expression, and you will obtain the value of 47/27. So the coordinates of the point are 2/3, 47/27. Okay, so that takes us to exercise 9i.